Okay, I can begin. Yes, okay, so first of all, I'd like to thank Michele for organizing today. It seems really fun. Also, welcome Carsten and apologize to him that I can't be there in person. If I recall, we last saw one another probably last summer at the Ensemble DFT workshop in Durham, where I think I last saw you at the Duke of Wellington pub when we were having pints together. So yes.
Oh, yes, that sounds about right. Yes, cheers.
Yes, yeah, yeah. But as many of you know, and as the title of my talk suggests, oh, first of all, can you see my pointer just to double check?
Yes.
Yeah, okay. Okay. As you know, I for my PhD, I came from a nonadiabatic dynamics group. And those of us in the field in nonadiabatic molecular dynamics knows that you can break the field up into sort of two ingredients, the nuclear dynamics and the underlying electronic structure. And of course, there are a number of methods in both of these categories. However, it was shown within the last couple of years, or sort of highlighted more explicitly, that actually it's the accuracy of the underlying electronic structure that can have a much larger impact on the accuracy of the overall non-adiabatic dynamics. And in particular, one sort of important aspect in non-adiabatic molecular dynamics, which a number of popular electronic structure methods struggle to describe, and Carson would have heard a similar talk that I gave last year, is the description of conical intersections. Points of degeneracy between two or more potential energy surfaces. Now, formally, conical intersections are comprised of an F- two-dimensional seam space, where F is the number of nuclear degrees of freedom of the system, and a complementary two-dimensional branching space. The branching space is characterized by these two key nuclear coordinates, the gradient difference vector G and the derivative coupling vector H. And it is only along these two specific nuclear coordinates that the degeneracy is lifted. It does so linearly to first order, giving this characteristic double cone shape. If you move along any of the remaining F-2 nuclear coordinates, the degeneracy is retained and the molecule stays within the seam space. Now, in particular for non-adiabatic molecular dynamics, but also in general, one should consider the topology of a conical intersection as well as its topography. Topology simply refers to the dimensionality of the intersection. So whether we do indeed get a conical F-2 dimensional intersection as shown on this slide here, or whether we simply get sort of two intersecting surfaces, hopefully you can see my hands, where you get a linear F-1 dimensional intersection. Topography refers to the sort of shape of those potential energy surfaces in the vicinity of the intersection. Now, of course, I did my PhD with David Tozer in Durham and Basile Kirchhoff now in Bristol. And of course, I'm here at Rutgers with NIPA. So I'm interested in time-dependent density functional theory, in particular linear response. And of course, it's been known since the early 2000s that linear response TDDFT struggles to correctly describe conical intersections involving the ground state. More recent work has sort of explicitly shown that linear response TDDFT does a good job at describing conical intersections between two excited states, although that perhaps was already sort of realized in the literature before, but maybe not explicitly shown. And then there's some work, of course, really exciting work by Davoud and NIPA of this year that sort of showed that if you include double excitations using Drist time-dependent density functional theory, you can actually correctly get the curve crossing of the infamous butadiene molecule. But I'm for this talk, and as again the title of the talk suggests, I'm focusing on the ground to excited state case, and I want to try and revisit it. In order to do that, we choose a test case molecule, of course, protonated formaldamine, so that's CH2NH2+. And for this talk, all we need to know is that the photodynamics typically of protonated formaldamine is characterized by two conical intersections, an excited to excited state conical intersection and a ground to excited state conical intersection. And again, our focus is the latter. Now, of course, in order to understand the description of this ground to exciter state conical intersection in TDDFT, we must explicitly plot their branching spaces. But you can already get a sort of feeling for perhaps something's going wrong by looking at these one-dimensional plots, where we see that the S1 surface, or sorry, curve in this case, is much more, the gradient is much more extreme near the degeneracy point than in our XMS Caspity-2 case. I forgot to mention just some, bookkeeping, that in our TDDFT calculations, we always use the Tam-Dankov approximation, and we take our reference method to be XMS Caspity-2, a well-known multi-reference method. Okay, so these are 1D plots. Let's actually look at the explicit branching spaces. So we see that, unsurprisingly, our reference method, XMS Caspity-2, correctly gives a conical F- two-dimensional intersection where the degeneracy is lifted along both of the branching space directions. TDDFT, perhaps again, unsurprisingly, doesn't. It gives a linear F- one-dimensional intersection. Now, if we look at the bottom of this plot, which is a color map of the energy difference, so red being positive excitation energy and blue being negative excitation energy, white showing the intersection seam. When we first looked at this plot, we were perhaps expecting a strictly linear plot, a seam, just because we're so zoomed in so close to the optimized crossing point. But in fact, we got this curve. And maybe it's not a surprise. We maybe should have expected to get a straight line or a curve, but nonetheless, we thought perhaps there could be something of interest happening beyond the extent of this plot. So we extended along the branching plane by a factor of 3 on the x direction and a factor of 30 along the y direction. Just note these x and y coordinates are just orthonormalized versions of the g and h coordinates that I showed on the second slide. Now we see that this sort of linear intersection along the standard branching plane is actually just a much smaller part of a much larger intersection ring along this extended branching plane. So that's interesting. We're not seeing an infinite linear intersection, but we're actually seeing a ring and something slightly more reminiscent to maybe a point of degeneracy. So yes, so we see this, we have an intersection ring and not a truly linear intersection. How does the physics of this intersection ring compare to that of a true conical intersection? So from a ring of intersection, compare that to a point of degeneracy. Well, there's one way to sort of confirm whether you have a true conical intersection, and that's related to the topological phase. And we can see that if you calculate this integral along a closed path, if that closed path encircles a conical intersection, it should return a value of pi. If it does not encircle a conical intersection, you should get a value of 0. Okay, more strictly and perhaps more generally, you should correct that first statement by saying if the closed path encircles an odd number of conical intersections, degeneracy points, then you should get a value of pi. If it's you enclose an even number of conical intersections, you should return a value of 0. Now, this is important for our case, given that our intersection ring can be thought of as perhaps an infinite number of degeneracy points. And so perhaps it's not so clear what value this integral should take. Now, I know a number of people in the audience have already seen a couple of these slides, so they know what's coming up, but those who haven't, this is for you. If we define then a closed path for XMS Caspity-2 and then a couple of closed paths for TDDFT, we see that our XMS Caspity-2 reference correctly returns a value of pi for calculating that integral along this closed path that encloses the degeneracy point. However, no matter how we define the path for TDDFT, so completely enclosing the intersection ring, it's hard to see, but there's a green path that is completely inside the intersection ring, or any variant of path that crosses the intersection ring, they always return a value of pi, of course, within numerical error. To numerical error. So we've got the incorrect topology, we have an intersection ring, and it's not correctly describing the topological phase. But the sort of extra conclusions, I guess, from this talk is related to actually running non-adiabatic dynamics, and in particular, I would say the most popular non-adiabatic dynamics method, and that's trajectory surface hopping. Now, this method does not actually consider the topological phase. Also, classical trajectories within surface hopping never reach a true degeneracy point at the point in which they hop. So, if we can perhaps assume that this region of problematic topology, or this ring of intersection, is sufficiently localized in space, does it really matter that it's incorrect when we run non-adiabatic dynamic or surface hopping dynamics in practice? This point can be sort of illustrated or by replotting the extended branching plane, but rather than along the strict branching space vectors, the x and y vectors, we try and reproduce it with two natural distortions. So a CN bond stretch and a twist around the central CN bond. And we see we reproduce the intersection ring quite well, and that it is confined to a relatively, a reasonably small region in configuration space, 0.02 angstrom by 0.04 degrees. So this point can be hit home, the sort of localized nature of this intersection ring, if we then instead plot the, say, let's absolute potential energy surfaces. And we see now, if we zoomed out far enough, so we're going from 0 to 180 degrees now, and a bond stretch of, say, 1 angstrom, we see that this intersection ring, from this view, from what the trajectory is seeing as it's coming in, looks as though it's a single point of degeneracy. However, we can't be too optimistic. If you zoom in only slightly, you see that we, and again, hopefully I don't give people vertigo, but let me try and zoom in. You see that slight penetration then begins to appear. Also from this slightly zoomed in plot, we see that, yes, okay, the ring of intersection is maybe localized to a small region of space. We get this exaggerated topography of this S1 state, which was clear or sort of was inferred by looking at that 1D cut. Okay, let me just get back. Okay, but let's see whether that extreme topography has any impact in practice. So I'm going to show you one trajectory using fewer switches surface hopping. And I'm going to consider two ways of doing fewer switches surface hopping. So the standard way, using analytic gradients, as well as using approximate Bekan couplings. And I suppose the motivation to look at Bekan couplings is because there have been a number of papers that have sort of benchmarked their performance, but their use is when, firstly, you're using an electron extraction method that can't give you formal non-adiabatic coupling vectors because there is no formal wave function. Or if you perhaps want to machine learn these quantities, it's easier to machine learn energy quantities rather than the cusp-like nature of the non-adiabatic coupling vector at a conical intersection. So we see that it depends on the curvature of the energy gap. Okay, so let's first have a look at fewer switches standard. So I compare XMS Caspity-2 trajectory to a TDDFT trajectory. And we see that our XMS Caspity-2 trajectory hops around successfully around 20 femtoseconds. And we see that there is a slight discontinuity in total energy, and that can be explained by looking at a zoomed-in plot of the potential energy curves or surfaces, and we see there is a slight discontinuity in the XMS Caspity-2 electronic structure. However, in this case, it has not affected the trajectory hopping because it hops sometime later. If, however, we look at now a TDDFT, we see that we have an unsuccessful hop at the same time as XMS Caspity-2 hopped. We have another unsuccessful hop, and then it's only around 70 femtoseconds we see a successful hop. The unsuccessful hops are accompanied by large jumps in total energy, peaks in kinetic energy, and can be sort of explained by the sharp topography, these cusp-like parts of the potential energy surfaces at these points. When we got a successful hop in TDDFT, the S1 surface behaved much more, or sort of behaved itself much more, let's say. But why are we not getting hops at these 2 points? Well, it could be obvious to you, but let's have a look explicitly. Well, we see at those 2 points, we get needle-like non-adiabatic couplings with very small integratable area, in comparison to when we got this successful hop in XMS-CASP-2 and in TDDFT, where the integratable area is larger, and given that the non-adiabatic coupling vectors enter into the equation for determining the probability of a hop, we see that if the non-adiabatic coupling vectors are problematic, then it's not going to result in a hop. Okay, but let's have a look at so that's standard viewer switches with analytic couplings. If we now look at Bekan, so it's interesting. So for XMS-CASP-2, we now see that this slight discontinuity in the energy actually results in a hop. Now, erroneously, let's say, it's not too problematic in this case, given that the states are already close together, and so the hop would have likely occurred only a small time later. But say we had the same situation and the surfaces were much further apart, then that would be completely unphysical. In our TDDFT case, we see, despite having this problematic sort of sharp cusp-like nature to the potential energy curve or surface, we do get a hop with Bekan, but we actually get an immediate hop back up to S1 and then a hop a little bit later. So that looks a bit weird. Why are we getting a hop in this case? Well, if we take a look at the couplings, we see, even though, okay, so this is a zoomed in picture of this plot here, and the orange is the analytic couplings that we saw on the previous slide. So the brown is now the new Bekan couplings. So even though the Bekan couplings are also needle-like, like the analytic couplings, their magnitude is 20 times larger. And so even though I made the argument that for the analytic couplings, the integratable area was small, this is outweighed by just the sheer magnitude of the Bekan couplings for TDDFT. Now, it's been shown in the literature before that Bekan couplings can generally overestimate analytic couplings, but I think I'm safe to say this is the first time that somebody has, or people have shown this for when you have a problematic electronic structure method, such as TDDFT. Okay, so I think that's everything I really wanted to discuss with you today, but a short recap. So we revisited the ground to excited state case. We see that we have the incorrect topology. We get an intersection ring. Unfortunately, that intersection ring doesn't pick up the correct topological phase. We could be naive perhaps in thinking, well, this intersection ring is localized in space, so perhaps it won't be of any problem in practical trajectory surface hopping. But of course, even though the intersection ring, this region of poor topology, is localized in space, the topographical implications are quite far-reaching. We get these cusps in the potential energy surfaces that then give rise to needle-like non-adiabatic couplings. And then, even though there has been motivation to investigate or to use these Bekan couplings, extreme caution should be taken when applying them in cases where the electronic structure has problems. I would like to acknowledge Basile and David, my 2 PhD supervisors, and of course, Nipa and our group, and everybody here for listening, and thanks for your time. Hopefully I didn't cut out.
Do we have time for 2 questions?
I have a question. So in condensed matter physics, what we often do is when we deal with the band gap problem in DFT, so you do an LDA GGA band structure, which tends to be too small. And then we use what's called the scissors operator cut it and then just make it a bit higher so that the band gap is better. So now I could argue, all right, we have your conical intersections, which are like the two cones sort of
interpenetrating,
and you get this ring intersection. So let's just take a scissors, cut it, and raise one of the cones so that you have tip on tip the way it's supposed to be in a conical intersection. So you have like, what was that? That was the topography. So you can somehow by hand set that right. But then that still doesn't fix the topology, correct?
Well, I think it would be the...
Which is the one, so you have the right geometry of it, but then you still mess up that phase factor.
So I think, so if I understand you correctly, if you were to do that shift and you would go from a ring of intersection to a point of intersection, that would correct the topology. And perhaps there would be argument to think if you did that, well, no. You would maybe think if you got the topology correct and got a point of degeneracy that you could then regain the correct topological phase. But I would think that my gut would be that you wouldn't get the correct topological phase, even if you did shift it to get a point.
Right. I mean, I wouldn't see why you get that.
It's an energy shift. The topological phase is a property of that range.
Exactly. But maybe when you do that, you get a little bit of an insight into what is actually happening. So what is it that makes it so special that gives you that phase? So when you just shift it, whereas when it comes out naturally from the degeneracy and the multi-reference nature of your states of the conical intersection. So I don't know, have you ever tried just doing that and just seeing what happens then? Because you've got these two sources of error. One is the ring instead of the point, and the other one is the phase factor. And that way you could eliminate one source of error, right? And see what the other one, maybe you see it more cleanly than what the effect of the phase is. I don't know if that makes sense.
Jack, you go ahead and give some comment if you answer.
Yes, I don't know whether, so, okay. So my gut feeling or my understanding is that, okay, yes, you could add a shift to the energy, but that would not affect this quantity here. So this nonadiabatic coupling vector. And I would guess that this the nonadiabatic coupling vector has a much stronger dependence on the quality. You know, it seems almost slightly cheating. You could get, let's say you could improve the picture of the two energies or the two states, the electronic states, but I don't know whether you'd pick up the correct physics. That seems just to be an artificial shifting. I don't think you would be correcting what is the problem, or what could be the problem, which relates to, again, the cone sham, a single cone sham determinant not correctly describing this multi-reference region.
Yeah.
Does that make sense? I know that's,
Sure.
Well, what was you're going to add something, Nipa?
No, I would agree with everything you said, and also just maybe also add that from the point of view of dynamics, what's also important are the slopes of the surfaces, right? And the shift won't affect that. So, for example, we're still getting really exaggerated. TDFT is giving I guess you call this the topography, right? It's giving. Yeah, the shape of the surface exaggerated, so we still have that issue. Which, in some sense, one might think, oh, perhaps it's a cancelling effect because then maybe things like couplings will be stronger, even though we don't have E minus, the vanishing denominator and at the conical section itself. So maybe this compensation, but no, it doesn't. I'm not sure if it really works like that. Yeah.
So vice versa, if you had that ring intersection, but the phase was right. Would that be advantageous? I don't know.
Yeah, I mean, sorry, Jack, go ahead.
No, I would say it would be perhaps advantageous to methods that consider the topological phase. It would maybe give a more formal confidence that the description, whatever that is, that TDDFT is giving, is not as problematic as what we're seeing here. But certainly for well, I can't speak for quite just yet because I am still learning. But maybe maybe stuff that Evaristo. Oh no, Evaristo, you won't consider the topological phase in your work, right? So I was going to say broadly, for anything related to surface hopping dynamics, you don't consider the topological phase, so it wouldn't be that big advantage in practice. But maybe maybe somebody's going to correct me in the audience, perhaps.
No, I think that's true. People do tend to ignore it.
All right, well, let's thank Dr. Taylor for the interesting presentation.
Thank you for having me.
Next up, we